Hello students, I am Professor NAVNEET KAUR from EC Department, SIRT College. Today I will be taking lecture on subject Digital Communication. The topic of my lecture is Flat Top Sampling Technique. In my previous lectures, I have already discussed the concept of sampling and the type of sampling, which is natural sampling. We already know that sampling is done to convert continuous time signal into discrete time signal. There are two types of sampling techniques. First is natural sampling, which we have already covered in our previous lecture. And the second technique is flat top sampling. In natural sampling technique, we have already seen that the amplitude of the carrier pulses varies according to the amplitude of the message signal. And here the top of the pulses follows the curvature of the message signal. But in in natural sampling, during transmission, when noise is introduced at top of the pulse, the amplitude of the signal gets affected, and the signal which we get is in the form of a corrupted signal. But in flat top sampling, this noise on the top of the pulse can be easily removed. Here the top of the samples are flat, that is they have constant amplitude, so they are known as flat top sampling or also called practical sampling. In flat top sampling, the top of the samples remain constant and equal to the instantaneous value of the modulating signal at the start of the sampling. Thus, the amplitude of the pulse after sampling is kept constant, and the top of the sample pulse do not follow the contour of the modulated signal, which is usually done in natural sampling. Now, we'll consider the generation of the flat top sample signal. The flat top sample signal is generated by convolution of the instantaneous sample signal with the non-periodic gate pulse. Here we can see in the figure, HT is the non-periodic gate pulse and X delta T is the instantaneous sample signal. Both these signals are shown in time domain. Now, when we consider the convolution of these two signals, we will get a new signal ST, which is the flat top sample signal. Here we can see the amplitude of the carrier pulses varies exactly according to the message signal, but here the top of the samples are flat. Now we will consider the mathematical analysis of the flat top sampling technique. Now here we have seen that ST, which is flat top sample signal, is given as HT in convolution with X delta T. Now X delta T is an instantaneous sample signal, so it is represented by expression summation k is equal to minus infinity to infinity xkts delta t minus kts. And rest of the equation is shown as such HT, and ST is given as the convolution of HT and X delta T. Now, X delta T, which I have already shown, it is XKTS delta T minus KTS, where K is any integer. We can represent this integer by K or F. So here we have seen that X delta T is given as X and TS delta T minus NTS. Now, X delta T in convolution with HT, according to the convolution formula, is given as minus infinity to infinity X delta U HT minus U du. Now, we will take X delta U from this equation only by replacing small t by small u. So here we will take integration minus infinity to infinity. Instead of X delta U, I will write this equation by replacing small t with small u. So I'll get summation X and TS delta U minus NTS HT minus U du. Now, since X and TS is having a constant value because it is defined at integral multiples of TS, we can take it out of the integral sign. So the summation X and TS is taken outside the integral sign, and here Inside the integration, we will get delta u minus nts ht minus u du. Now we already know the shifted property of delta function, according to which if we'll take summation, if we'll take integration of any time dependent signal with the shifted impulse signal, we will get the value of the signal which is defined at the point where this impulse function is located. Since this impulse function is located at t is equal to t naught, so we will get f t naught, where t naught is the point where this impulse function is located. Now, using this property and using the previous equation, now when I'll consider this integration, I have seen that this impulse function is located at nts. So when I'll evaluate this product, I'll get that this ht minus u will be evaluated at u is equal to nts. So here I can see I'll get summation x nts ht minus nts. Now if I'll analyze this equation, I'll get here st in terms of sampled value x nts and function ht minus nts. That means here the pulses are located at every integer multiple of ts, that is 0, ts, 2ts, minus ts, minus 2ts, and here the amplitude of each pulse is varying according to x and ts. So I will get the pulses located at every interval of ts and each having amplitude of x and ts. That means the amplitude of the message signal at every ts. Now, here we will see the electronic circuit which is used to generate the flat top sample signal. Now, here I'll consider the combination of two switches S1 and S2, where S1 is called sampling switch and S2T is called discharge switch. Now, at the instant where the pulse begins, the switch S1 closes. It closes to sample the modulating signal. When this switch S1 will close, the capacitor will charge towards the input voltage xt. Now, since the forward resistance of the switch is very low, the capacitor will instantaneously charge to this voltage x2. The capacitor C holds the sampled voltage for period tau. At the end of this period tau, which is the end of the pulse, this switch S2 is closed. Now, when the switch S2 will close, the capacitor will get a path to discharge. So, capacitor will discharge through this path where the switch S2 will be closed. Now, since the forward resistance of switch S2 is very low, the capacitor will instantaneously discharge to the zero voltage and the pulse will goes to the low level. Thus, the signal generated as a result of this circuit is a flat top sample signal. And this circuit is known as sample and hold circuit. Now, here we have seen the two waveforms in which the waveform A represents the message signal xt, B represents the instantaneous sample signal, C represents the train of the pulses, and D represents the flat top sample signal, which is obtained by convolution of ht and x delta t. Now, we will talk about the limitation of the flat top sample signal. Now, when we will consider the spectrum of the flat top sample signal, we will see that the amplitude of the flat top signal must be constant. But sometimes it is not constant due to high frequency roll-off of the sample signal. This results in the attenuation in the high frequency part of the message spectrum. This distortion results from the fact that the spectrum is multiplied by sampling function sine x upon x, which is the Fourier transform of the non-periodic gate function. So here we'll see that the flat top samples, the spectrum of the flat top sample signal, its amplitude will go on reducing and there will be the distortion in the signal. This aperture effect can be improved by selecting value of the pulse width tau to be very small or by using equalizer circuit. Equalizer circuit is a circuit which is having transfer function which is reciprocal of the or inverse of the sampling function sin x upon x. When this equalizer will be connected in cascade with the reconstruction filter, which is actually a low pass filter, then the signal will be restored to its original form and we will get the message signal which is very close to the original message signal which was transmitted on the transmitter side. The combination of this equalizer and this low pass filter is known as composite filter. And this effect of distortion is known as aperture effect, and the equalizer is used to remove or minimize the distortion due to the aperture effect. Now this is all for today's lecture. Thank you.